In this video, I want to talk about what happens in the linear programming model when we remove a decision variable or when we add a decision variable. So it is part of the sensitivity analysis, but we will be doing it, at least in part, without using the sensitivity report that's provided by solvers. So when we remove a decision variable, the first thing we have to ask ourselves, what was its optimal value? So if we removed the decision variable was actually 0 in the optimal solution, then the remainder of the optimal solution, right, the remaining variables can still be equal to the same values, and the optimal objective function value will stay the same, right? The variable was 0, so if we remove it, we're like removing zeros from all constraints and from the objective, so nothing really changes. However, if the optimal solution, in the optimal solution, the removed variable had a non-zero value, it may be positive, maybe negative, then the optimal solution will change normally, and then the optimal objective function value will normally worsen, right? However, it is also possible, however unlikely, that the optimal solution will stay the same and the optimal objective function value will stay the same. It might, for example, happen when we have multiple optimal solutions. So why is this working like this? Well, it is working this way because removing a variable from a model is equivalent to adding a constraint on this variable, a simple constraint, xi equals 0, right? So if we're adding a constraint, if you recall, this is like a restriction of a model. And in the restriction, we know that the optimal objective function value might become worse or it might stay the same. So basically those two cases are cases of what happens if we restrict the model, right? So let's consider two examples of removing decision variables. First example, what if x1 is removed from this model that you see here on the right? So if this is a model, a profit maximization model, a product mix type of problem, where we have 3 products to produce, we maximize profit subject to 3 resource constraints, and the variables can take values between 0 and 150, and the optimal solution is given here, and the optimal objective function value is 83,000, right? So first thing to notice is that in the optimal solution, right, the x1 star had a value 0, right? So if x1 is removed, right, the optimal solution will be the same as before, right? Except that, of course, this first variable is no longer a decision variable in a modified model, so the first value will also not appear, but this solution should still be optimal, right? And the optimal objective function value will still be $83,000, right? Okay, a second question, what if x2 is removed from the model? And actually, removing x3 would have similar consequences. So if x2 is removed from the model, we have to see in the optimal solution, x2 is equal to 50, right? It's not 0, so it is not 0, right? So if x2 is removed, right, the remainder of the optimal solution, right, this part that remains, right, which will be x1, x3 equal to 0 and 150, this solution might change, might no longer be optimal, although it could still be optimal, right? That's why I'm saying might, but most likely it will not be optimal, and the optimal objective function value might become worse, right? Because we just removed a variable So we just applied a restriction, right? As if we said x2 equals 0. And now we cannot have x2 50, so this optimal objective function value might become worse, although we could say, or it might stay the same in general. Actually, in this case, it's very likely that it will become worse because we had a variable with positive profit contribution, and therefore, if we shut down production of the second product type by having x2 equal to 0 enforced, we're very likely, it is very likely that we will reduce the optimal profit in this model, so it will become worse. Okay, so we considered removing a decision variable, and we said this is as if we restrict the model by adding a constraint. This removed variable equals to 0, and you will see if we add a decision variable, it will be like a relaxation, provided that 0 is a feasible value for the new variable. So first thing you have to see is 0 a feasible value for the new variable, and typically it is. We usually add variables with non-negativity or some upper bound, right? But what I mean feasible, I mean that it is the lower bound for the new variable, 0 or less, and the upper bound 0 or more, right? In that case, the old optimal solution supplemented by 0 as the value of the new variable will still be feasible, right? We can guarantee the old optimal solution plus 0 for this new decision variable will be a feasible solution. However, we want to ask ourselves, will it be still optimal, right? And to know if it will be still optimal, we need to find calculate a reduced cost for this new decision variable. And if you recall, a sensitivity report provides reduced cost for all decision variables, but those decision variables that of course exist in the model. And now we're adding a new decision variable that previously was not in the model, so the reduced cost is not available. However, surprisingly, reduced cost can be calculated for this new decision variable without resolving the problem, provided that we assume this decision variable is at value 0, right? So for example, if it has a lower bound 0, we could say we can calculate its reduced cost for increasing the lower bound 0, right? So for example, how do we calculate it? Well, the formula is this. The formula says, take the objective coefficient for this new decision variable, and subtract the sum of costs of constraints when you value those constraints at shadow prices. So for example, in a product mix, it would be profit contribution as the objective coefficient, and minus the total value of consumed resources when you price those resources at shadow prices. And I want to emphasize, this works, these formulas work for any decision variable in the model and also for any variable that you potentially want to add, assuming this new variable is equal to 0, right? So if we do this, if we find the reduced cost, if the reduced cost for this new decision variable is positive and the objective is maximization, then what does it indicate? It indicates that if we were to increase this new variable above 0, right, for example, by pushing its lower bound 0 up, we would improve the optimal objective function value, right? Positive reduced cost means increasing by 1 the variable will increase the optimal objective function value by reduced cost. This is the marginal value of increasing the variable, right? And by analogy, if the objective were minimized and the reduced cost would be negative, then increasing the lower bound, the variable, would decrease the objective, which would also be good because in minimization we want to decrease, right? So in this case, right, we would know it's a good change, right, to increase the variable above 0, and that means we would have an improvement. The solution would improve. The optimal objective function would improve if we did increase. If, however, reduced cost for this new variable were negative, and this is the maximization objective, and by analogy, if it was positive and this was a minimization, then decreasing, right, this is increasing, would be improving the optimal objective function value. Here, decreasing would be improving the optimal objective function value. And then, of course, if there is a lower bound, typically lower bound would be equal to 0. If the lower bound is equal to 0, we can't really decrease below 0. That would mean that the variable will stay at 0 and it will not change. So the old optimal solution would be the same, right? Now, in both of those cases, notice that we don't have range of feasibility, right? We can calculate the reduced cost for the new decision variable. And if it's positive, for example, and the objective is maximization, we know, we can improve the objective function, optimal objective function value by increasing the variable above 0. However, we really can't be sure we will improve because we don't know how long it is, right? The range in which the reduced cost works. And it might be that this range is such that allowable increase for this lower bound of the decision variable is actually 0, right? So we wouldn't really get the improvement in the optimal solution, optimal objective function value, despite having positive reduced cost. That's why we can only say that the optimal solution might change, and then the optimal objective function value might improve, right? But it is still useful to do this exercise, because if we find out the reduced cost is negative, well, definitely increasing the variable will not improve the optimal objective function value, right? And of course, we need to consider the fact that if reduced cost for the new variable is 0, this is like the model is indifferent to increasing or decreasing the new decision variable. So that means the old optimal solution should still be optimal, and the optimal objective function value should still be the same, right? And what I said before is that this change is in fact equivalent to adding a new, right? Adding a new decision variable is actually equivalent to a relaxation of the model. Why is that? Because we can imagine that the new variable is actually already in the model, but there is a constraint xi equal to 0, right? So, and then adding this variable is like removing this constraint xi equal to 0, right? So this situation of adding a new decision variable is equivalent to a situation where we already had the variable in the model with the constraint xi equal to 0, and now we remove this constraint, right? That's why adding a new variable is like a relaxation of the model. And one final thing I want to say is that this method of evaluating a new decision variable using reduced cost is actually a basis of a very useful solution method for linear programming models called the delayed column generation. So delayed column generation is a method that works really well when you have a problem with a very large number of decision variables. And if you have a very large number of decision variables, maybe you cannot even generate the model because it would be too large. It would have too many decision variables. And also, if you recall, in the constraint matrix, for every decision variable, there is a column in the A matrix, right? So in that case, the solution method, the delayed column generation method, what it does is it starts with a subset of decision variables initially, and then when it solves the problem with this subset to optimality, it gets all the sensitivity information, and then it asks the question, is there another decision variable that I didn't generate initially, but I should add that would improve the problem, the solution, right? So what does it do? It actually finds a new variable that satisfies something like this condition. Finds a new variable, if this is a maximization objective, if it can find a new variable that has coefficients in the constraints and the objective such that the reduced cost for the new variable is positive, then it knows adding this decision variable and the corresponding column to the A matrix, to the constraint matrix, will actually result in an improvement of the optimal objective function value. So then it adds this decision variable and resolves the problem, and then again asks the question, do we add another decision variable or not? That's delayed column generation, right? This is, of course, not a complete description, but just a link if you are interested. The basis of the delayed column generation is actually this method of evaluating decision variables, potential decision variables that we could add to the problem. So let's consider now an example of adding a new decision variable and evaluating it. Suppose we have this model, a product mix model with two decision variables, x1, x2, profit maximization, and three resource constraints. And again, because we will be using them, I extracted here from sensitivity analysis reports the shadow prices for the three constraints that we see. We also know the optimal solution, 122.78, and the optimal profit, 66,100. So before we actually go for adding a new decision variable, let's just see that the formula for reduced cost, which we provided before, which is, right, if you recall, objective coefficient minus sum of constraints, of costs of constraints valued at shadow prices, or for this particular problem, you can use the second formula, right? The product mix, it's profit contribution minus total value of consumed resources priced at shadow prices, right? What would it be here? We can say that the reduced cost for the first variable, for x1, what is it? It has an objective coefficient 350, so profit contribution or objective coefficient is 350, and then minus, how many resources does it use? It uses one pump, so it's 1 times shadow price 200, right? Plus, it uses 9 labor hours times shadow price 1667. It's actually 16 2/3 if you want very accurate calculation. And plus, and it uses 12 feet of tubing at shadow price 0, so it will be 12 times 0. Obviously, this will be 0, right? So it's 350 minus 200 plus, and if you do the calculation exactly with 2/3 instead of this 0.67, you'll get 150 and plus 0, right? So you get 350 minus 350, 0, right? And if you recall, when we were solving this problem earlier for sensitivity analysis questions, we had reduced cost for the first variable, 0, and then reduced cost for the second variable is very similar, right? The objective coefficient is now 300 minus, and then actually I can copy this part because shadow prices will be the same, but resource consumptions might be different. It's still one pump, but it's 6 labor hours and 16 feet of tubing. So it's 6 and 16, but the shadow prices remain the same, right? So it's 300 minus 200 plus, and again, if you take 6 times 16 and 2/3, you'll get exactly 100 and 0. So the second reduced cost is 0 again. And of course, this is because the variables here were not equal to the lower bounds, and there were no upper bounds. So reduced cost in this case, as you recall from sensitivity analysis, reduced cost in such case has to always be 0. However, if we had another decision variable, let's say that would be equal to 0, then its reduced cost would most likely be different than 0, and we could see it here, right? So now the question that we want to consider: what if a new product is introduced, and this new product has profit contribution 320, right? And resource consumptions are 1 pump for every unit of this new product, 8 labor hours, and 13 feet of tubing, right? What can we say about this? So this would be like introducing a new decision variable, right? We could call it x3, since the first two variables were x1, x2, right? And then what's surprising, like I said, is that we can calculate its reduced cost, 3, the same way as here, right? So we have to take, I'll copy it and correct. We need to take 320 as the profit contribution, because that's what we get here. And then 1 times 1 pump is used still, but 8 labor hours and 13 feet of tubing, I need to change 8 and 13, but the same shadow prices can be applied. So if this new variable x3 is 0, the reduced cost would be, right, would be equal to 320 minus, and this is 200 plus 133.33, right? So it is actually 320 minus 333.33, right? And that is minus 13.33. So it's a negative value, right? It's a negative value. So what? So given that I'm assuming that the lower bound would be 0, right? And this negative reduced cost tells us we would like to decrease the variable x3, because increasing it actually would increase the profit by minus 13. It means it would actually decrease it. And if we decreased x3, we would decrease the profit by minus 13, and decreasing by a negative value would mean increasing. So we have an incentive with this reduced cost to try and decrease decision variable x3. But if it is at 0, we can't decrease it more, right? So what we can say is, right, so we can say decreasing the new variable would improve the optimal objective function value, right? However, since the lower bound for x3 equals 0, right, the variable cannot be decreased below 0, right? So the optimal solution, right, that we had, the old optimal solution supplemented by this new value x3 star equal 0 will still be optimal, right? And the optimal objective function value will still be 66,100, right? So this is, of course, the case where the reduced cost in the maximization problem, right? We have maximization. If the reduced cost is negative, we would like to decrease the variable below 0, and if the lower bound is 0, then we can't, and that means this product, if we introduce it, so the business interpretation would be, if we introduce this product, it's not going to be produced because the alternatives, these other original two products, are actually better use of resources for maximization of the profit. However, it's very easy to imagine that, let's say if I assume this slightly higher number, like it's even 340, and I put 340 here, 340 here, 340 here, right? There would be 340 minus 333. It would mean there would be a positive reduced cost. And that would mean increasing this decision variable would improve the optimal objective function value. And then, of course, we would say the optimal solution might change and the profit might increase above the 66,100. So this was a video about removing and adding decision variables from or to a linear programming model.